Albert Einstein developed special relativity, although other scientists had previously done important work. There are two basic premises. 1. The laws of physics are invariant in all inertial frames of reference. Inertial frames are equivalent to constant velocity. And 2. The speed of light in a vacuum is the same for all observers regardless of the light source or observer motion. This is known as the principle of light speed invariance. Although Einstein stated both propositions formally, they both suffer from incomplete explanations. Premise 1 is concerned with Newtonian mechanics and does not venture into the realm of the speed of light. Premise 2 seeks to open Newtonian mechanics to the speed of light, but suffers from the inadequate description of the absolute reference frame in which light is measured. That frame is the cosmological reference frame, abbreviated CRF. Light is not subject to the moving reference frame from which it is generated. Light travels at 3 × 10⁸ meters per second, designated c by physicists, in the CRF. For instance, if we are traveling in a rocket at 1/2 c and shine a light in front, that light is not traveling at 1½ c. Light is subject only to the CRF. Moving frames that generate light offload their radiation fronts to the CRF. Examples of moving subreference frames from which light is generated or received include the Earth's movement around the Sun and the Solar System's movement in the galaxy. All these variable movements add and subtract within the CRF, but the net effect is a small fraction of the speed of light. The CRF defines space as an immovable canvas, where all matter, like stars and planets, move about within. The CRF did not show itself in the experimental evidence of the Michelson-Morley experiment because the transmitters and reflectors were moving in unison. The CRF might be considered ether, but it is fixed in place. Everything in space moves relative to it. Special relativity also suffers from its utilization of the 90-degree reference point, which excludes all other reference angles. This is the Lorentz factor. It is a huge deficiency. Shown here is the conceptualization of field establishment for a fast-moving object. The field in view is electric for a charged particle or gravitational for a mass object. A traveling wave moves at the same velocity. They move or establish their fields at the speed of light. For a very fast-moving charged object, shown here as 95% of c, the electrostatic field in front is significantly shorter compared to that of the resting object. The resting object is red at the center. The reach of the field is the length of the blue line. The blue line length is divided by the distance light travels in the same time. The result is the field strength multiplier. The field strength multiplier causes a field reach reduction in front of a moving object. Conversely, the field behind a moving object is stretched. The real Lorentz factor is simply the inverse of the field strength multiplier. The observation angle dependent formula is more complex than the 90-degree limited Lorentz factor. The result is the modified Lorentz factor, designated gamma mod. Color shift is a simple application of relativity. Its understanding depends on the correct application of the modified Lorentz factor. Here there are two observers. One is fixed in the CRF and the other is traveling behind the source at the same velocity. An observer moving at the same velocity as the source would see an accurate color scheme. This is the same configuration as the Michelson-Morley experiment, since the light generator and light receiver are moving together. An observer fixed in the CRF would see a red shift. If the relativity superbulb is employed, a trailing observer will see a blue shift because he is scooping up radiation fronts quicker by traveling through their advance. A fixed observer would see the real color because the radiation time spacing is preserved in the CRF. Time dilation is a consequence of the finite nature of the speed of light. Time dilation is similar to color shift, but it does not apply equally to all moving transmitters. Observation angle is critical. If the observed object is moving away, there will be a perceived time dilation of the transit time. If it is approaching, there will be time compression. Length contraction was postulated by applying the unmodified Lorentz factor to traveling objects. It is easily disproven with the theoretical employment of a relativity superbulb. Relativity superbulbs can simultaneously offload a single wavelength at the fore and aft of a moving ship. That wavelength enters the CRF and travels to the observer. A CRF fixed observer will see no angular variation depending on ship velocity. The side view of a fast-moving object using a standard AP transmitter might not even be visible. For approaching and receding views, both transmission types will yield identical length measurements. The mass increase argument was the other spurious application of the Lorentz factor. At the time of its proposal, there was no way to test it. With the subsequent inventions of particle accelerators and bubble chambers, it was easily disproven. If this effect were conclusively demonstrated, relativistic mass would be a part of every physics curriculum. Relativity is only an information science. The observed object is not undergoing any physical alteration just because the observer perceives it. Color shift and time dilation or compression are valid observations. The space-time world-line interpretation, which requires that any fast-moving object, regardless of its direction of movement, age more slowly, is fallacious. Length and mass alteration are disproven. Relativity places no speed limit on an object. The infinite mass at the speed of light argument was once proposed as the primary reason an accelerator cannot breach this velocity. As a practical matter, no object can ever attain light speed due to lesser considerations. 1. Rocket propulsion is very limited due to the slow speeds of chemical combustion and the large amount of reactants needed. 2. Light propulsion, as conceived with lasers or sails, is a minute effect that is also limited by the speed of light. And 3. External Pauling propulsion, like that of a charged particle in an accelerator, is limited by the object's capability to project an electric field in front of its position. At near light speed, there is no handle with which to pull it any faster. Nevertheless, relativistic mass was used to derive the most famous formula in physics. Mass-energy equivalence and its theoretical sibling, the energy-momentum formula, need relativistic mass to be true. This is an outline of the mathematical steps used to derive mass-energy equivalence and the energy-momentum formula from relativistic momentum. Start with relativistic momentum, which is relativistic mass multiplied by velocity. Momentum is the velocity derivative of kinetic energy. Integrating momentum yields kinetic energy, which is our objective. Force is defined by a change in momentum over time. Integrate that force over a distance to obtain the work done on an object. This is the kinetic energy from a standing start. Change the integration limits from distance to velocity by employing the chain rule. We are left with relativistic energy and rest mass energy. Square the relativistic energy component to derive the energy-momentum relation. As stated previously, relativistic mass rests on real shaky ground. Most physicists disregard it. Nevertheless, relativistic energy is still defended. Rest mass energy has been central to modern physics for 100 years. There are three significant problems with special relativity. The first is the Lorentz factor limitation of the 90-degree observation angle. The second is the relativity fallacy of a moving object undergoing any physical alteration like time dilation regardless of the path of travel. Finally, the application to unproven realms like length and mass. The real damage to special relativity was opening the time-based Lorentz factor to non-time-related aspects of physics. General relativity depends on the disproven aspects of special relativity and asserts the gravitational distortion of space. The idea is that mass alters the contours of the flat space of special relativity. Special relativity is, therefore, a subset of the general theory in areas where there is no mass. In the general theory, space itself is configured, and everything will follow the space-time geodesic described by that reconfiguration. That includes light, which attains mass properties via mass-energy equivalence and the energy-momentum formula. It also includes time, which under heavy gravitational load is slowed down. The Euclidean space of CRF-based special relativity is superseded by exotic notions of Riemannian manifolds and very complex mathematics. The nonlinear field equations contained in the Ricci and metric tensors cannot be solved. Computed solutions can be undertaken when some variables are eliminated. Mathematical creativity can be unleashed to describe singularities such as black holes, unusual transport schemes like wormholes, and theories like the Big Bang. General relativity suggests that light would be subject to continuous gravitational redirections in its travel across interstellar space. The interstellar warpage would vector light far off a linear course, such that astronomers would be looking through a carnival house of mirrors, unable to discern logical patterns in the cosmos. These concepts were developed purely mathematically and contain singularities which are an anathema to physicists. Painstaking efforts are still being made to prove them with observations. Observations of the light bending of celestial bodies, where light passes very close to stars like the Sun, are more likely explained by the standard refraction through their gaseous atmospheres. Alternate explanations can be found for the perihelion of Mercury and other problems consigned to general relativity. Ultimately, general relativity is an exotic attempt to redefine Newtonian gravity. Gravity has a certain mystique that grips physicists. Why do two objects sitting in space need to attract each other? The nature of the problem is almost metaphysical. Electric fields are easier to rationalize and accept. Much effort has been expended to further the fantastic claims of general relativity without realizing that the foundations of the science were poorly defined, the mathematics was limited to a single viewpoint, and expansion to non-informational realms is invalid. Both special and general relativity are burdened with numerous errors, and a century of development has overlooked the foundational weaknesses of the sciences. A far simpler elaboration of the concepts, minus the logical errors, would yield CRF causation dynamics. Nature prescribes the CRF for the light speed establishment of fields generated by mass and charged objects, as well as radiation caused by linear acceleration of charged particles. Objects with interacting fields motivate each other in real time.